Hello everyone, this is Dr. Zach. For today's lesson, we're going to look at the role of integration in the study of work. If an object moves a distance d, we define work to be equal to F times d. Now, if it's a linear force or just a linear distance, we just do multiplication and life is easy. So the first question shouldn't be any challenge. The second question, you're going to have to worry a little bit more about your units in order to make your comparison. Go ahead and do that. Let's focus on the units in these problems. For Sophie's problems, we have measured in pound-feet. Pound was your force, so pounds is a unit of measurement for force. And feet, of course, is your distance. This is your British engineering system. Now, when we look at Vasily's problem, your problem was measured in pound meters. So we've mixed the standard international system with the British system, and that's kind of weird. So for question B, in order to solve this problem, you probably want to make certain that you have found either everything in centimeters or everything in meters. But again, the pound is the measured force. So what's the difference between force and mass? Force is the push or pull on an object, and we saw from our previous problems that that's going to be measured in pounds. So pounds, again, is a force, whereas mass is the amount of material. An example of mass measurement would be kilograms, and kilograms is mass. Now, mass is not a force, but we know that force is equal to mass times acceleration. And if that's true, when we're measuring in the standard international system, the acceleration that we're going to use is negative 9.8 meters per second squared. So if we want to figure out the force when we're in the standard international system, that's going to be our mass, which might be kilograms, multiplied by negative 9.8 meters per second squared. That is going to be the measure of force, kilogram meters per second squared, when we're in the standard international system. Now, is all force constant? No. If you take another look, we were moving in a linear direction. So that linear direction was either horizontal or it was vertical when we were thinking about questions A and B. Is all force constant? No. Think about how much work it is to pull a spring or to push a spring. And also think about gravitational pull. It's much more challenging to get a rocket off the Earth than it is to fly the rocket once it gets out of the atmosphere. So let's talk about our units. Newtons are going to be the units that we use when we're in our standard international system. Now, we talked about this, but the units for mass is going to be a kilogram. So a Newton is measured in kilograms, then that is going to be multiplied by the force required to move it, which is 1 meter per second squared. So a Newton is measured in kilogram meters per second squared. Whereas if we look at the British engineering system, now we already said that pound is a force. So a pound, the mass of a pound is actually measured in slugs, and you have 32.1740 of them make a pound. So one slug of acceleration has feet per second squared in it. So they took their slugs, they multiplied by the gravitational pull, and we're left with pounds. So in the British engineering system, pounds is going to be our unit of force. So work is force times distance. So in the standard international system, we take our newtons and we multiply it by meters. Once again, what was a newton? That was going to be your kilogram meters per second squared, but then we multiply it by meters again. And so now we've got kilograms meters squared over second squared, and that is equal to a joule. Whereas in our British system, a foot multiplied by a pound is our going to be equal to the work, and the work is measured in foot-pounds. So the standard international system needs a little bit more work to get the units in place than your British system. We have some conversion factors. I've listed these here for you just in case you need them. You will not use those on your AP exam, but I do like you to have a complete set of notes. Not all force is constant, and therefore not all work is constant. So we have a couple of laws to help us out. Now, Hooke's law, right here, force is equal to K times D, is going to help us when we are thinking about working with springs. So if we compress or stretch a spring, and then we're going to use F equals KD, where D is going to be the change in length from the original length. Then we have Newton's law of universal gravitation. So if we have two masses, they're going to be the force is proportional to your two masses, but it's inversely proportional to the square of the distances between your two particles or masses. But we're going to take these three constants, put them together, and just call them one constant, since this is calculus. And if we take a look, Coulomb's law is doing the same thing, except we've got two charges instead of two planets. So the force is equal to K times 1 over D squared. Now, suppose we take this object, it's moving in a positive direction along the coordinate line over the angle AB, while being subjected to the force F of x. Now, F of x could be a variable, it's got a variable x in it. Then work is defined as the integral from A to B, F of x dx. So when we're looking at our problem, you want to think about what work is being measured in and what distance is being measured in, because you're going to have to set up each one of these problems. Take a moment to read your first question, and we will begin. For your spring problem, you want to start by drawing your spring at its natural length. Notice the labels that I've chosen. The spring is at its natural length 10 centimeters. So I started my numbering system at 0 on the right and negative 10 on the left, because I'm going to be stretching my spring from 15 to 18 centimeters. Since we have a spring, we're going to use Hooke's law. So force equals K times D. We know that we were given information that a force of 40 newtons was required to force our spring to be stretched from 10 to 15 centimeters. So the difference between those, or the distance between those, is going to be 5 centimeters. Substitute in your 5. Wait a minute, that was centimeters. But centimeters is not how we measure newtons. If you'll go back to recall, newtons were measured in meters squared per second squared. So we don't want centimeters, we want meters. Change the 5 to 0.05, then we can solve for K. And K is equal to 800. Now that would be newtons per meter. But when we substitute it back in, we have our force is equal to 800 D, where we're now measuring in newtons again. Now the purpose of this problem was to solve for work. We want to know the amount of work done to stretch our spring from 15 centimeters to 18 centimeters. So again, we're going to have to switch that into meters. So a slice of work, so delta W, is going to be equal to the force that's done, so F of x, multiplied by the amount of change. And if we're going from 0.15 meters to 0.18 meters, we're going to have to adjust those numbers for our number line that we've drawn. And if we adjust those numbers, it's going to be 0.05 and 0.08 when we think about our number line. So our delta F is going to be equal to F of x times our delta x, where delta x is traveling between 0.5 and 0.8, and that gives us our endpoints. So F of x is now replaced with 800x, and then our delta x is, of course, dx. So the amount of work done is going to be given to us by this lovely equation. How are we going to measure this? We know that 800x is newtons, so final units need to be newtons, and dx is measured in meters, so we have Newton meters, but Newton meters are just another way to say joules. So once you complete this problem, you will know how much work is done in stretching that spring from 15 centimeters to 18 centimeters. Emphasis again, your slice of work in this problem is equal to F of x times delta x, where delta x is the amount or distance that each one of the slices along your axis moved when stretching that spring. Take a moment to read over this problem. Now, as you read the problem, what I'd like you to understand is that the drawing of your problem is one of the most important aspects. We have an inverted cone, and once you draw your inverted cone, it's important to place your figure on an XY axis so that you can write equations for the different problems that you're working on. In this particular problem, we're going to let the vertex be where the X and Y axis intersect, and this will be 0, 0, or our origin. We also know that the cone is 10 feet tall, so the point on intersection on your y-axis is going to be 0 with 10. All right, so why is that important? We're also told that we have the radius is 4. So if the radius of our cone is 4, we have another value, which is going to be 410. And from this value, we can write the equation of the line joining 0, 0, and 410. We know that that will be y equals, and the slope is up 10 over 4, so we have 10 over 4, or 5 over 2x is the equation of our line. All right, so now let's think about the water. The water is filling up our cone from the 0, 0 all the way up to our 0, 8. And we want to take all of this water and force it out of our cones. We're going to take a slice of water. Now, let's not consider the top slice. Let's just find a slice of water. Let's call it this one right here. And we want to force that water up and out of this inverted cone. So if we're slicing up the water, we know that that's going to be delta y, and we can also use delta y in order to find different aspects for this problem. So we could find the volume for that slice of water. All right, let's do that. Since it's a slice, we know that delta V for one slice of water is going to be the area, which is pi r squared, multiplied by the delta y, and that will make it volume, measured in meters cubed. So we're now in meters cubed, which will be useful to know. Well, what is the radius of that circle? The radius is actually your x value. And if we solve for x, we know that x is equal to 2/5 y, and we can replace the radius in our problem as pi 2/5 y quantity squared delta y. So one slice of volume is going to be equal to our pi times 4 over 25 y squared delta y. All right, so we now have a slice of volume, which is going to end up to be helping us, I hope. So let's go back to what we're looking for. We're looking for work. So a slice of work is going to be equal to a slice of force multiplied by distance traveled. What we have right now is volume, but let's go back it up even a little bit more. We know that force is equal to some sort of weight. And weight is mass times acceleration. But mass is equal to density times volume. Well, there's our volume. So the density of water is 1,000 kilograms per meter cubed, multiplied by the volume that we came up with for our slice. And the slice, once again, was 4 over 25 pi y squared delta y. All right, now before we get too far, let's talk about units again. The density of your water is kilograms per meters cubed multiplied by the volume, and the volume is meters cubed. So the mass, you can see, is kilograms, so we're right on target for getting what we need. Okay, so delta F. Delta F in this problem, we want to know the force it takes, or the weight of that water, which is your mass times your acceleration. Well, your mass was your 1,000 times 4, so there's our 4,000 over 25. Here's our pi y squared. I'm going to throw my delta y over at the end because, we don't like to have delta y in the middle. And we're going to multiply that expression by acceleration. But what is acceleration? Acceleration for weight is the gravitational pull. Now, you know that the gravitational pull is negative 9.8 meters per second squared. But because we want the force and the the force and the work to be positive values, we use positive 9.8. Okay, again, let's talk about units. So we now have this constant that's occurring, but that was kilograms meters cubed times our y squared delta y, so that's meters cubed. Then we multiplied it by acceleration, which is meters per second squared. Put all the units together, and we are left with kilogram meters per second squared, and that, of course, is force. All right, so work, a slice of work is going to be equal to a slice of force multiplied by distance. The distance that we're referring to is the distance that your slice has to move up and out. So this is the distance that your slice moves. And when we look at our picture, go back to that lovely picture, your distance is going to be some arbitrary value of y. The slice moves upward and out. So we're going to do a top minus bottom idea for this. So our distance is going to be equal to, the top value is 10 minus where the slice occurs, and that is y. So the distance the slice moves is going to be 10 minus y. So now the integral work equals the integral of our force, which is your 4,000 divided by 25. Then we'll have our pi, y squared. We're going to multiply it by 9.8. We have to multiply it by the distance that the slice moves. There's my 10 minus y. And then our delta y, which is going to be changed into dy. All right, now let's talk about endpoints for a minute. So the endpoints are describing where the dy values occur. Now the dy values in our problem is where we have the water slices. Your water slices in this picture are all going between the 0 and 8. So when we look for our endpoints, we're going to be integrating between 0 and 8. Again, let's talk about units because I am obsessed with getting these units correct. All right, so we now know our final units. We have the y, which is going to be meters squared. We have 10 minus y, which is meters again. dy, which is meters. We have 9.8. The 9.8 is acceleration, which is meters per second squared. But then we also have to multiply by density, and density is kilograms per meters cubed. Double check that everything cancels out. We have our meters squared, meters cubed, meters. Our final answer, once you figure it out, is going to be kilogram meters squared over second squared. And we know that these are the units that make up joules. So we have completed our problem correctly. Find that value and you are set. Look through this problem again, then begin your lesson follow-up.